In this video, we'll look at the Compton effect. In 1923, in an experiment, Arthur Compton showed that photons carry momentum as well as energy, and they are subject to the same conservation laws of energy and momentum as other more familiar particles, like we have seen before. Now, in his experiment, he used X-ray photons. What are X-rays? X-rays have a wavelength ranging from 1 nanometer to 0.001 nanometer, and this wavelength is approximately 500 times shorter than that of visible light. Therefore, these will have higher photon energy. We know the formula equals to hc over lambda. Here lambda is the wavelength. Since wavelength is smaller, therefore these X-rays have higher photon energy than the visible light. X-rays were discovered in 1895. This is the sketch of a modern medical X-ray tube. A potential electrons are ejected from the heated cathode on the left. Then a several thousands volt of potential difference of several thousand volts between cathode and anode accelerates these electrons, which therefore require several kilo electron volt of kinetic energy. X-rays are produced when the electrons crash into the anode and are brought to an abrupt stop. It is found that most of the rays are emitted near 90 degrees to the electron's path, and for this reason the anode is usually tilted to encourage the X-rays to exit in one direction, as shown. Unable to identify this radiation, he gave it the name X-rays. Now, the ability of these X-rays to penetrate solids of low density was put to medical use within few months of their discovery, but the problem of identifying what X-rays really were took longer. Now, using this X-rays, Compton did the experiment. Now, when X-rays are directed towards materials, they are scattered by materials' loosely bound electrons. And early studies of scattering of X-rays showed that X-ray scattering happened without change of wavelength. The classical theory of such scattering is straightforward. The incident wave has oscillating electric field and magnetic field. Such oscillating electric field of the incident light causes the charges of the material, for example the loosely bound electrons, it causes the charges to oscillate, and the oscillating charges then radiate secondary waves in various directions. The angular distribution of these scattered waves depend on the detailed arrangement of the target charges. But one prediction of the classical theory is common to all targets. That is, the frequency of the scattered wave must be same as that of the oscillating charges, which in turn must be same as the incident frequency f0. So the frequency of the incident wave should be same as the frequency of the radiating wave. And because frequency is same, the scattered wave should have same wavelength as incident wave, but with less energy. Now, numerous experiments using visible light to do such scattering measurements and preliminary observations with X-rays, they all seem to confirm this prediction. However, starting in 1912, there appeared various reports that when high frequency X-rays were scattered off by electrons, the scattered frequency was actually less than the frequency of the incident wave. So the scattered X-rays contain wavelength of the incident rays and new wavelengths. Again, classical electromagnetic theory totally failed to explain such new wavelengths or the presence of such new modified wavelengths. In 1923, American physicist Arthur Compton published two papers in which he argued that if light is quantized, one should expect to find that f is less than f0, or that the frequency of the scattered radiation is less than that of the incident radiation. Compton argued that if photons carry energy, they should also carry momentum. So, scattering process is analyzed simply as an interaction or like collision between a single photon and a single electron which is at rest in the target. So we will see what happens if such a photon collides with an electron at rest. So initially, for a photon, energy can be written as hc over lambda, and its momentum can be written as energy divided by c. And for electron, that is in the target material, since the electron is at rest, initial velocity is 0, and hence energy is only the rest mass energy given by me. E is a subscript here, c square, and momentum is also 0 because velocity is 0. Therefore, initially or before the collision, when photon is moving towards electron which is at rest, total initial energy can be written as E plus mec square. And since electron was not moving, total initial momentum is equal to p, which is the momentum of the photon. Now look at this scattering process very carefully, and you will see that this photon collides with this electron at rest, and so that the photon goes in one direction making an angle theta, and electron is scattered in a different direction making an angle phi. So initially the photon has energy E and momentum P, electron has energy mec square and momentum 0. The scattered photon is represented to have energy E prime and momentum P prime, whereas scattered electron has energy E subscript E and P subscript E. So now all we have to do is find what these values are and use the conservation of total energy and conservation of momentum. So after scattering, this electron will have energy and momentum of electron will be Pe. Now this momentum is can be resolved into two directions because it's making an angle phi with x-axis. So it can be resolved into x and y components. And these are the x and y components of the moment of scattered electron. Momentum of scattered electron. Using law of conservation of total energy, we get initial energy is equal to final energy. So we get our first equation. And because momentum is in two direction, we will use equations in x and y direction separately. So here is equation for x-axis, and for along y direction we have also momentum conservation. So here for y-axis initial momentum is 0 because neither photon nor electron was moving along y-axis. We can rearrange equation 2 and 3 to get these two equations. Now we can simply square and add these two equations here, this equation and this equation. We can also write, so we know this equation is true for energy of an electron, which we call it now equation 5. So we can substitute equation 1 in equation 5 and also in equation 4. We can just keep solving it. We get this energy equation, and if we want to convert it into the wavelength equation, we get. Now this equation is very important. Here lambda prime is the wavelength of the scattered photon and lambda is the initial wavelength of the incident photon. Therefore, I can write lambda prime minus lambda as delta lambda, which is the Compton shift. This was first derived by Compton. Now there are few things to notice in this important equation, Compton shift equation, is that first, it does not depend on the initial incident wavelength. I'm talking about the Compton shift does not depend upon incident wavelength. It does not depend upon the scattering material. It only depends on the scattering angle. So here this formula gives the increase in photon's wavelength when it is scattered through an angle theta. Since delta lambda is greater than 0, therefore wavelength is always increased and frequency is always decreased. Now if I plot intensity as a function of wavelength, and let's say here the red curve represents my incident wavelength, then for scattered intensity versus lambda diagram, it will depend on the scattering angle as we have seen in the formula. So let's say when scattering angle is 45 degrees, you get incident wavelength and also some modified or increased wavelength for scattered radiation. Here wavelength is shifted a little bit. Now if the scattering angle is 90 degree, if you plug in the equation, the shift in wavelength will be much larger, and the larger shift in wavelength can be easily seen when theta is 90 degree. Now if the scattering angle is further larger and it is 135 degree, then we can clearly see that delta lambda is increasing. So just remember that scattered radiation does not carry only increased frequency, but it carries same wavelength as the incident wave. As you can see, all these have incident wavelengths also, plus modified wavelengths. If we plug in the values of H, mass of electron, and C, we can get this equation, and here wavelength shift is in nanometers. We can clearly see that when theta is equal to 180 degree, then we get the maximum shift in the wavelength. And that is because cos of 180 degree is equal to -1. By substituting, we can actually calculate maximum shift in wavelength to be equal to delta lambda equal to 0.004852 nanometers. Just remember, the Compton theory holds true for the free or loosely bound electrons of the atom or a material. If the electron is tightly bound, then whole atom can recoil, and then whole atom recoils, and mass of in this formula, mass will be mass of the atom. Since mass of the atom can be very large, delta shift will be very small or negligible. Therefore, in heavier elements, no change in wavelength is observed. It's very important. Now, if I ask you a question that would you observe change in wavelength or shift in wavelength when X-ray hits a proton? Answer would be no, because mass of proton is much greater than mass of electron. So again, in the denominator you have a heavier mass, so delta lambda shift will be much smaller. Another question you can think about is, can you observe this Compton effect with visible light? Answer again would be no. Since energy of visible light quanta is not large enough to remove electron from the material to give scattering. In other words, wavelength of visible light, which falls in the region 400 to 700 nanometer, is about 5,000 times larger than that of Compton's X-rays. Therefore, the fractional change delta lambda by lambda naught is about 5,000 times smaller than for visible than for X-rays. Now, if we have to find what is the direction of scattered electron, we can go back to our equations. Let's say equation 1, if you remember from the previous slide, and rewrite that as, now since the scattered electron is moving, it will also have a kinetic energy and a rest mass energy. So from this equation we can get the kinetic energy of the scattered electron as equal to E minus E prime. So kinetic energy acquired by scattered electron is equal to the difference between the initial and final energies of photon. Now we can find the direction using this formula. And now we can substitute the value of momentum of photon. So from here we can get the direction of the scattered electrons if we know the initial and final energies and the scattering angle of photon. Now let's look at a question that in a particular Compton scattering experiment, it is found that the incident wavelength lambda 1 is shifted by 1.5% when scattering angle theta is equal to 120 degree. First is what is the value of wavelength lambda 1? Second, find out what will be the wavelength lambda 2 of the scattered photons when scattering angle is 75 degree. So in this equation of Compton scattering, we can directly substitute the value of theta to calculate change in wavelength. Now it was found that the incident wavelength is shifted by 1.5% only. That means delta lambda divided by lambda 1 is equal to 0.015. So from in this equation you can actually calculate lambda 1. Now for part B, scattering angle is 75 degrees. So we can substitute 75 degree in the equation, but now we also know lambda 1. So we can easily calculate lambda 2, which is equal to 0.245 nanometer. And hence we solve this problem.